Alright, this video will be over logarithmic functions. First, we need to go over the definition for a logarithmic function. Alright, the definition for a logarithmic function with a base a, where a is greater than 0 and it's not 1, is denoted by y equals log base a of x. And this only happens if and only if you can take the base, raise it to a power of y, and set it equal to x. And the domain of the logarithmic function of base a is the same as the range of the exponential function with the same base, and that would be all the values greater than 0. Alright, now I want to point out why you can rewrite the logarithm as an exponent. Alright, remember, exponential functions and logarithmic functions are inverses. So, like on the right hand side, you have to rewrite it as an exponential a raised to a power of log base a of x. The a and the log base a cancel out, so that's how you end up with the x. But what you do on one side, you have to do to the other, so you'll have a raised to a power of y. That's where you get the a raised to a power of y from. That's why they can be rewritten in this manner. Alright, it says change each exponential statement to an equivalent statement involving a logarithm. First one, 1.2 raised to a power of 3 is equal to m. Alright, that would be logarithm, log, and the base of the exponent would be the base of the logarithm, so log base 1.2 of whatever it's equal to. M is equal to whatever the exponent is, which is 3. For B, remember, since it's e raised to a power of b is equal to 9, it'd be log base e of 9 is equal to b. And for part C, since you have a to the 4th is equal to 24, it would be log, then whatever the base is, which in this case is a, then the thing it's equal to, which is 24, that goes on the inside of the logarithm, so it would be log base a of 24 is equal to whatever the exponent is, which is 4. Here are a couple more examples. Change each logarithmic statement to an exponential statement. For the first part, log base a of 4 is equal to 5. To change it to an exponent, the base would be the same, so of log base a, the exponential function would also have a base of a. So it would be a, and then whatever it's equal to, that becomes your exponent. And then the input of the logarithm is what the exponent is equal to. So for part B, we take the base, which is e, then whatever it's equal to, which would be negative 3. That's the exponent, and then the input of the logarithm, that's what the exponential is equal to. So for part C, that's log base 3 of 5 is equal to c. So it'd be 3 take the base of the logarithm and the base of the exponent are the same, and whatever the logarithm's equal to, which in this case is c, there's your that would be your exponent, and then the exponential function is equal to the input of the logarithm, so it's equal to 5. Alright, here are a couple of examples. It says find the exact value of these two logarithmic expressions. So for part A, remember, you can set it equal to y or x or whatever. So that means 2 to a raised to a power of y is equal to 16. Remember, 16 can be rewritten as 2 to the 4th, which means y would be 4. Because if 2 to the power of y is equal to 2 to the power of 4, then that means the exponents would have to be equal, so that's why y is 4. Now for this one, for part B, our base is 3, so you can take 3 raised to the power of y, so that's equal to 1 over 27. Remember, 27 is just 3 to the third power. 1 over 3 to the third. And 1 over 3 to the third can be rewritten as 3 to the negative third. That tells you that in this instance y is negative 3. Now we're going to learn how to determine the domain of a logarithmic function. Here are a few notes you need for that. Remember, the domain of a logarithmic function is the same as the range of the corresponding exponential function. So, like, if you have a logarithmic function log base 2 of x, the corresponding exponential function would just be 2 raised to the power of x. So the domain of this logarithmic is the same as the range of the exponential, and the range of the logarithmic is the same as the domain of the exponential. Or to put it in shorthand notation, the domain is from 0 to infinity, and the range is the set of all real numbers for a logarithmic function. Alright, here's some examples. Find the domain of each logarithmic function. Part A says f of x equals log base 2 of x plus 3. It says the domain is the set of all positive numbers, meaning the input, which in this case is, instead of x, our input is x plus 3, that's greater than 0. Which means our domain would actually be all the x values greater than negative 3. If you want to write this in interval notation, it'd be all the values from 3 to infinity. That's what it means by domain. It's just whatever you have for the input of the logarithm, it has to be positive. Alright, so for part B, log base 5 of 1 plus x over 1 minus x. Pretty much you have to take the input and find out where the input, which is this rational function, is greater than 0. Alright, since we have a rational inequality, you have to find where the numerator is equal to 0. Remember, numerator is equal to 0 at x equals negative 1. And denominator is equal to 0 at positive 1. See, we cannot have it being equal to positive 1, because if it's positive 1, that would make the denominator equal to 0. And we can't have it be negative 1, because if it's negative 1, then the numerator would be equal to 0, then that would make the entire thing equal to 0. And we want all the values that are strictly greater than 0. So now pick a number in each interval. Like, pick a number less than negative 1, say negative 2. If you were to plug in negative 2, it would be 1 plus negative 2 all over 1 minus negative 2. So it would be negative 1 over 3. So if you pick a number from this interval, you'll end up with a negative number, so we don't want that. So pick a number between negative 1 and positive 1. You could choose 0. So instead of 1 plus x, you can try 1 plus 0. And then instead of 1 minus x, it would be 1 minus 0, so it would be 1 over 1, which is positive. So that works. That interval works, but we have to check the other one. Pick a number greater than 1, say 2, and plug it in for x. 1 plus 2 all over 1 minus 2. That'd be 3 over negative 1, which is less than 0. We don't want that. So the only interval that works would be from negative 1 to positive 1. We can write that in interval notation. Or you could say all the say all the values such that -1 is less than x, and x is less than +1. Either of these would work. For part C, log base 1/2 of the absolute value of x. You have to find where the input is greater than 0. Now, if you notice, absolute value is always greater than 0 at every value except for 0. So the domain would be all the real numbers except that x cannot be 0. Or, to use interval notation, be from -infinity to 0, union with from 0 to infinity. All it does is skip over the x value of 0. And now we're going to learn how to graph logarithmic functions. Alright, since logarithmic functions and their corresponding exponential functions are inverses, you can take the exponential functions that we learned about in the previous video and you can just flip it across the line y equals x. For instance, you see the blue graph that looks like the exponential functions that you learned about in the previous video. And you see if you just flip it across the parent linear function y equals x, you get the corresponding logarithmic function. Remember, this is when our base is greater than 1, such as if you had y equals 2 to a power of x, and the constant is positive. Alright, and when our base is a fraction, whenever our a is between 0 and 1, the graphs of the exponential and corresponding logarithmic functions would look like this. As you can see, the blue function is our exponential function with a fraction as the base, or as the growth factor. And the corresponding logarithmic function is in red. As you can see, they're still reflected across the line y equals x. Now I have a couple of examples to show you here. Now you notice here, if you graph the exponential function 2 to a power of x, you have the points -1, 1/2, 0, 1, and 1, 2 that we discussed before. But the inverse, remember, with an inverse function, the domain and the range flip. The domain of our original function becomes our range of the inverse. In the range, the y values of the domain, the y values of our original function become the x values of our inverse. So if you notice, if the point -1, 1/2 is in our original function, the point 1/2, -1 is on the graph of our inverse because the domain and the range switch. Likewise, if you were to graph an exponential function with the growth factor as a fraction, like 1/3 raised to a power of x, it's the same principle. You'd have -1, 3, 0, 1, and then plug in 1, you'd get 1/3. Since the domain and the range switch for the inverse, instead of the point 1, 1/3, on the inverse you'd have the point 1/3, 1. Instead of the point 0, 1, you'd have 1, 0. And instead of the point -1, 3, you'd have the point 3, -1. So now we're going to discuss some properties for the generic function log base a of x. First off, the domain for a logarithmic function x is just the set of all positive real numbers. That's when it's just x for the input. It's not like x minus 4 or whatever. And the range for any logarithmic function is just the set of all real numbers. Now the x-intercept is 1 as opposed to the y-intercept for the exponential function. Remember, the domain and the range flip since they're inverses. Now, the y-axis is a vertical asymptote for the graph, as opposed to the x-axis being a horizontal asymptote like in the exponential function. Now, a logarithmic function is strictly decreasing if our base is a fraction, and it's increasing if it's a number greater than 1. Now, assuming there's no constant in front, assuming it's just log base a of x, these 3 points are on your graph, 1, 0, and wherever your base is, with 1 as the y coordinate, and then 1 over your base, and -1. And the graph is smooth and continuous. Alright, before we get into an example, I want to quickly go over the natural log function. Remember, you may have seen this function, y equals ln of x. This is only true if you can rewrite it as x equals ln of, or x equals e raised to the power of y. That's because ln of x is the shorthand for saying log base e of x. Alright, something I want to point out. In order to undo any logarithm, would explain why you can rewrite any logarithm as an exponent. You just create an exponential function but use the same base. Because the e and the log base c will cancel out, so that's where you get the x from. So if you do it to the other side, you have e to a power of y. So that's just e to a power of y is equal to x. Alright, so here's a 6-part example. So find the domain of our logarithmic function f of x equals negative ln of x minus 2. Alright, so for part A, you have to take the input and find out where it's positive, because remember the input can never be less than or equal to 0. That means the domain would be all x values greater than 2. Or if you want to write it as an interval notation, be the interval from 2 to infinity. Alright, for part B, let's start with just ln of x. So you start off with just the graph of ln of x, and you have to multiply it by 1 to get negative ln of x, so that would just flip it across the x-axis. Like so. You see now how it's been flipped across the x-axis. And if it's x minus 2, that means the graph is shifted 2 units to the right, which would give you this as your final graph. Now it asks to find the range and the vertical asymptote. The range for any logarithmic function is the same as the domain for any exponential, so that'd be the set of all real numbers, or the interval from negative infinity to positive infinity. Now the vertical asymptote, if you notice, it never goes past where x equals 2. Because if it included 2 on the domain, that would make the input equal to 0. And by definition, the input has to be positive. So the vertical asymptote would just be the vertical line x equals 2. Now for part D, to find the inverse of f. Remember, that means find the actual equation for the inverse. Right. Now, you start off by flipping the x and the y's. I'm sure you remember this from previous math courses. That's the first step in finding the inverse. You switch the x and the y's because in the inverse, the domain and the range switch. That's why you flip the x and y's. Now, we have to get rid of this negative sign. To do that, you multiply everything by -1. So you have negative x is equal to ln of y minus 2. Now we need to get rid of the natural log. The natural log can be rewritten as an exponential function of e. If you raise both sides with the base of e, the e and the ln will just kind of go away because they're inverses, so you end up with y minus 2. Then on the left hand side, you just have e to a power of negative x. So to get the y by itself and thus to have the inverse, you would need to add 2 to both sides. So you would have that the inverse is equal to e to a power of negative x plus 2. For part E, it asks to find the domain and range of the inverse. Remember, the domain of the inverse is the same as the range of the original function. So the domain of the inverse, I believe, would just be the set of all real numbers, because that's the same as the range of the inverse. And the range is the same as the domain of the inverse, so that would be the set of all values from -2 to infinity. And for part F, where it says to graph the inverse, all you have to do is take your original graph and reflect it across the line y equals x. Alright, so there's the graph. The blue graph is our original function, -ln of x minus 2. You can see, once you flip it across the line y equals x, you get the inverse, e to the power of -x plus 2. Now we're going to learn about the common logarithm. You may have seen something that says just y equals log of x. Remember, that's the same as log base 10. And that's why the common log can be rewritten as the exponential x equals 10 to a power of y. Because you take the base, which is 10, raise it to a power of y, and set it equal to the input. Alright, here's an example similar to the one we did before, where you're given an equation, f of x equals 3 log of x minus 1. You're asked to find the domain, then graph it, then determine the vertical asymptote, the range. Pretty much everything we've done before, except we're dealing with a form of the common logarithm instead of the natural log. So for part A, to find the domain, you take the input and find out where it's greater than 0. And that tells you the domain would be all values greater than 1. So to write it in interval notation, be all the values from 1 to infinity. Now to graph it, we can start off with our equation, with the equation just log of x. Alright, so this would be the equation, this would be the graph of just log of x. And you have to start off by shifting it 1 unit to the right since it's minus 1. And this would give you this graph. It's the same thing, just shifted 1 unit over to the right. And now you need to add, or you need to multiply by 3, because that just stretches it out by a factor of 3. Now it would give you a final graph of, it would give you this as your final graph. Now you're asked to find the range, and so remember, the range for any logarithm is just the set of all real numbers, or on the interval from -infinity to positive infinity. If you notice, for a vertical asymptote, and the domain never goes past the x value of 1. So since the domain never goes past there, there's a vertical asymptote at x equals 1. Now to find the inverse, you have to start with our equation, kind of like what we did in the previous example. 3 times the log of x minus 1. And you have to switch the x and y's, so you'd have x equals 3 log of y minus 1. Now you just solve for y. You need to get the log by itself, so you can divide by 3 or multiply by 1/3, and you get 1/3 x is equal to log of y minus 1. Now, since it's a common logarithm, the base is 10, so to get rid of the log, you rewrite both sides as an exponential with 10 as the base. Now on the right hand side, the 10 and the log cancel out, so you're just left with y minus 1, and you have 10 raised to a power of 1/3 x. So if you add 1 to both sides, you have that the inverse is just 10 to a power of 1/3 x, then plus 1. Remember, the domain of the inverse is equal to the range of the original function. So the domain is just all real numbers. The range is the same as the domain of the range of the inverse is the same as the domain of the original function. So it'd just be all y values greater than 1, or the interval from 1 to infinity. And to graph the inverse, you do the same thing that you did before, flip our original function across the line y equals x. As you can see in this screenshot of the graphs, we have our original function in blue, f of x equals 3 log of x minus 1. If you just flip it across the y-axis, you get the graph of the inverse. Alright, now we're going to go over how to solve logarithmic equations. Alright, so here are a couple of examples of different equations you can expect to solve. So for part A, whenever you have the logarithmic equations, like in parts A and B, you can rewrite it as an exponential. So that'd be, take the base, raise it to the power of whatever the logarithm's equal to, which in this case would be 2, set it equal to whatever the input is, which would be 4x minus 7. So that would just be 9 equals 4x minus 7. That should be a 7 up here. So now you can solve this for x. 16 is equal to 4x, which means x is 4. Now for part B, you can do the same thing, take the base, raise it to an exponent of 2, set it equal to 64. Which means technically if you solve it for x, x would be plus or minus 8. But remember, the base of a logarithm has to be positive. So the only one we're concerned about is the positive solution, x equals 8. Here's another example, solve e to a power of 2x is equal to 5. You can solve the exponential equations also by using logarithms. You can do log base c of both sides, or simply, to shorthand it, do ln. Do ln of e of 2x is equal to ln of 5. The ln and the e cancel out, so you have 2x is equal to natural log of 5. Which means if you solve for x, x is equal to natural log of 5 divided by 2, which is approximately 0.805 if you want to do it in your calculator. But this would be your exact answer. Alright, here's a word problem for you, because I know how much every math student loves word problems. It says blood alcohol concentration is the measure of the amount of alcohol in a person's bloodstream. A blood alcohol concentration of 0.04% means that a person has 4 parts of alcohol per 10,000 parts blood in the body. Relative risk is defined as the likelihood of one event occurring divided by the likelihood of a second event occurring. For example, if an individual with a blood alcohol content of 0.02% is 1.4 times more likely to have a car accident as an individual that has not been drinking. So that means the relative risk factor with the blood alcohol content of 0.02 is 1.4. Now, recent medical research suggests that the relative risk of having an accident while driving a car can be modeled by an equation of the form R, which is the relative risk, is equal to e raised to a power of k times x, where k is just some constant and x is the concentration of alcohol in the bloodstream. Now, I have a 4-part question for you. It says research indicates that the relative risk of a person having an accident with a blood alcohol content of 0.02% is 1.4. Find the constant k in this equation. So, you can take the relative risk of 1.4 and plug it into your equation. Remember, this is your equation. K times x. So plug 1.4 in for r. You have e raised to the power of k times our blood alcohol content of 0.02%. So now we need to solve for k. In order to do that, we can do log of both sides, since the log and the exponential are inverses. Now, on the right hand side, the ln and the e just kind of cancel out, so you have k times 0.02 is equal to natural log of 1.4. So now if you divide by 0.02, you have your constant. Ln of 1.4 over 16.82, which is or ln of 1.4 over 0.02, which is approximately 16.82. This is a lot easier to plug into our formula than this fraction, so we're going to use this, even though this is the more exact answer. So for part B, it says using this value of k, what is the relative risk if the concentration is 0.17? To do that, you need to plug that value of k in with x equals 0.17%. So our r is equal to e raised to the power of 16.82 times 0.17. Now since we rounded our constant, this would just be an approximation, so our risk factor is approximately 17.5. Or the relative risk factor is about 17.5 compared to somebody who hasn't been drinking. Now for part C, it asks, using the same value of k, what blood alcohol content corresponds to a relative risk of 100? So, here we have r equals 100, and our risk factor, or our constant, k. So if we plug those in, we need to find what blood alcohol content corresponds to this relative risk factor. So we can do ln of both sides, and it should simplify to 16.82 times x if you do that. So now x is equal to natural log of 100 divided by 16.82. which means that would correspond to a blood alcohol content of about 0.27%. And for part D, it says if the law asserts that anyone with a relative risk factor of 5 or more should not have driving privileges, at what concentration of alcohol in the bloodstream should a driver be arrested and charged with DUI? So here, pretty much is saying, if the risk factor is 5, what would the blood alcohol content be? So it's pretty much the same thing as before, but instead of 100 you use 5. 5 is equal to E, and then you have your constant of 16.82 times X. So, you have to do natural log of both sides. Do the natural log, and the ln and the e would cancel out on the right hand side, so that gives you 16.82 times x is equal to natural log of 5. So if we divide both sides by 16.82, that means that the concentration would need to be about 0.096%. That means that if the law does assert that anyone with a relative risk of 5 or more should not be driving, then their blood alcohol content would need to be about 0.096%.